Okay, so we start the third part. It's about entropy. Open quantum system, we ask questions of the kind, how long does the system take to thermalize? What are abstractions for thermalization? And entropy plays a crucial role in that. So the plan for this lecture is to look at entropy, at the definition, at one specific concrete definition of entropy and information. You have the slides. If you haven't checked, download them. I'm gonna use the slides and comment directly on the slides, okay? So what is the plan? I'm gonna first cover the definition of relative entropy, then connect it to a notion, information theory that gives it an interpretation, a direct interpretation. How do you test an hypothesis? And then I'm gonna use it first in classical mechanics and show you what you need to fix to apply it to quantum mechanics, okay? Sources, chapter 10 of the book that Preskill has been working on for, I don't know, 20 years now, is near perfection. So I really recommend checking this topic there. It's explained in a simple and immediate way. There's a standard textbook about all these aspects of quantum information, quantum computing, that is Nielsen and Chang. Check chapter 9 and 10. If you're interested in the really mathematical aspects of how one does this hypothesis testing, I love this book, PETS, Quantum Information Theory and Quantum Statistics. And there's a similar style version that is this mini intro of it. Is lovely to read, okay? So I want to start as concrete as possible. And one way of doing that is to start with a puzzle. So here's the puzzle. The puzzle is, consider this probability distribution, okay? Concentrated, some width. And the question that I have for you is, which one of these three is farthest away from this one? Maybe I can describe them so that it's easier to read. This one is a bit wider. This one has 2 peaks. This one has a few points up here. Make up your mind. I want to see a show answer so that you commit to one, and then we go through arguments. It's clear that the question is not fully well posed. I have to say more. So interpret the question. So which one is farthest away? How many A's? Okay. How many B's? Okay. How many C's? So 0%, 90%, 10%, I would say. Okay. And do you have an immediate comment before we go ahead? Like, for the kind, what do I mean, or how did you interpret it? Yes.
Maybe the mean and expectation, not the standard deviation.
Good. Yeah. So I somehow chose them so that they all have the same mean. It's this line at 10, but it's true that this one is wider. This one is also wider. Nobody said this one. But if you check the standard deviation, this one and this one have exactly the same standard deviation. So by that measure, these two would have been both okay. More comments.
You can also think about larger and larger moments.
Larger and larger moments
all
to detect this one. Okay, so they would distinguish these two. A comment on this one?
You need a lot of moments to get that one.
More comments? Yeah, Elliot.
Third, we're in this distribution, infinitesimal peak. I didn't think percent things very much.
Yeah, shouldn't matter. It's just a point or maybe a few points. How do you measure it? Still, it looks very different. So I have to say, what do I mean in a way that is useful? More comments? One more comment? Yeah.
More of a question than a comment.
Yeah.
If you actually knew the distribution, there are ways to compare it, but if you're actually performing experiments and sampling from the distribution, how would you do it?
Good, good. So at the moment, I'm just giving you plots. Then I'm gonna move to sampling, okay? And it seems that from the 90% of B, most of you have a sense that this one is the one that is most far away. The question is, what is that intuition capturing? And what I want to argue is that it's really entropy that is capturing. You are seeing something that has to do with entropy, with relative entropy of this one with respect to the hypothesis, this one, not the other way around, okay? So there's a follow-up point that I should make that is, say far away, but can you put a number? How far? This one is different from that. This one is different from that. But why did you say that this one is more far away than the other? What, by how much? Okay, is there a comment before we go ahead? Okay, so I'm gonna give you a list of notions of distances that is probably the ones that you had in mind, and then we can go back and look at this. So these are notions of distances between two functions, all things that you study when you study analysis. There is a notion, it's very standard, it's the pointwise distance. You take the difference of the functions in modulus, and you look at the soup. It's clear that this one is the one that is farthest away, because the soup is just here. It's like 0.3, while here it's way smaller, okay? But as Elliot was noticing, oh, but that's just a set of measured zero. If you have an apparatus, can it detect just a point? Measures things of finite measure. In fact, there's a notion that in mathematics is really about measure theory. That is to introduce a measure, for instance, a Lebesgue measure. Here, I'm looking only at this L2 measure. You integrate it. This one really checks things that have to do with, it neglects completely things of zero measure. So let me make these comments. First, yes.
Riemann.
It's a Riemann. Well, I want a Lebesgue integral. I want to make it make sense on measures. Okay?
But that one that you wrote there is Riemann.
I want it to make sense on functions that are not necessarily smooth, but yeah, you can take it as a Riemann. Okay. So if the soup of the distance is zero, they are the same function. There's no doubt. Everything becomes trivial. But if it's not zero, it doesn't tell us anything about the distance. While this measure theoretic one, if it's zero, it tells us that the two functions are indistinguishable as far as measurable quantities. But these are just notions of distances for functions. Here we are interested in a probability distribution. A probability distribution is more than a function. If you want, it has already properties of the kind, it's positive, it integrates to one. It's not just a function. A physicist way of looking at it is check dimensions. If this was length of something, the probability has dimensions of 1 over length. Those distances were all dimensionful. The soup is L to the minus 1. The distance with the square root, L to the minus 1/2. So this distance depends on the units that you're measuring, that you're using. That doesn't make sense. I didn't even declare if it was in meters or in centimeters, what I had done the plot before. So what is the meaning of that size? There was a comment, I forgot to add the comment on moments. What's your answer? Somebody had the comment on check moments. Check moments, they provide a better notion of distance. If it's near Gaussian, you check the first few, okay? I'm gonna give you a notion, yes?
Why the specification of it being near Gaussian?
If it's two Gaussians, you just check it by checking the standard deviation. If it's very far from Gaussian, you really have to go read it in all the moments. They might not even completely determine the distribution. Some of them could be infinite and still the distance between the distributions be finite. Okay,
Like partial distribution.
So,
Partial-
yeah. So for near Gaussian, this is a good notion. I'm gonna give you a definition that is the notion that I want to introduce and then motivate. This is the notion of relative entropy. So the formula is here. I'm gonna first comment and then we derive it from sampling, as somebody was asking. So what is this
Well,
formula? Yes.
Because I was thinking, you mentioned the moments. What characterizes a Gaussian is that all odd moments are zero, and all even moments can be written as
Yeah.
products of one, which is
Yeah.
the second moment.
Yes.
So that's it. So you, by comparing moments, you don't necessarily measure Gaussian, but you have to prove that the even moments can be decomposed in products of the two, the moment, second moment.
Take two probability distributions that are neither of the two Gaussian,
Yeah.
but close enough in the sense that the moments are close to the big ones.
And the cumulants then the thing we have to look at.
Yeah, but then you can compare them, and that will give you a measure of how far the two distributions are when the moments characterize completely the distribution. But if it has long tails, they are not good enough. Okay? So the notion that I'm going to give you now, this one is the one that I want to convince you that this is the relevant notion. So how do I convince you? First, I give you the definition. We do some checks, and then I derive it. So the definition is it's a function of my hypothesis, the probability distribution, the one that I gave at the beginning, and the one that I want to check how far is from the reference one. It's written in terms of a measure, so it doesn't detect just points, it's not pointwise. PDX is dimensionful. Log, inside the log, there should be always something dimensionless. Ratio of probabilities is good. So this gives you a sense of like why those things put together work well. The meaning that we're going to discuss in a moment is that this one is relative entropy of P with respect to P naught, measures the statistical distinguishability of P from P naught. The check of dimensions already did. There's a comment. When I say log, I always mean a log natural basis. I don't know, like Mathematica does. I don't write LN. Keep it in mind that this literature just oscillates between these things. So for me, log 2 is 0.69 approximately. Okay? And so if you ask about units, it's dimensionless, but you can really think of it as the number of natural units, or if you divide by log 2, the number of bits. Okay? It has names in the literature. Sometimes people call it relative entropy, sometimes Kullback-Leibler divergence, divergence of one distribution from the other, sometimes information gain, and you would measure it in bits. There is one more property that I think it's important to highlight. It's the kind of question you ask if you're coming from general relativity. Like, I could choose the coordinates that I want. So what if I change coordinates and I ask if the probability, how the probability transforms? Well, the probability is at density. PDX integrates to 1. So the probability has to transform with a Jacobian. But the distance between distributions, or the divergence of one from the other, should be independent from the coordinates. And this notion that we have there, it is independent. What's the mechanism? Well, PDX, this is good. And then this ratio, this is also good. The Jacobian cancels. Mathematicians call this radon derivative of measures. This is a measure, this is a measure. It's a differential measure, and it's the ratio differentials. And so sometimes they call this the average log radon derivative. Okay? So I've given you definitions. Are there comments before we go ahead? Yes.
Why is this a natural thing to write down?
I haven't said that. I'm going to illustrate it with some examples. And then I'm going to derive the formula from something else that is exactly what you were asking. Like, I don't want distances between functions. I want to know if I have a sample, how do I tell this sample from my hypothesis? Okay? Maybe 2 examples. So the first example is take your reference distribution that is a Gaussian, and the distribution you want to compare to that is also a Gaussian, but it has a different width. Okay? What is the relative entropy of P with respect to P naught? You just have to do this integral. It's easy to do. And you find that it depends only on dimensionless quantities that are the only one that is in the game, ratio of standard deviations. And you can check if the two are the same, this relative entropy is 0. The ratio is 1, the relative entropy is 0. And if it's larger, it grows quadratically, and if it's smaller, it diverges logally. Okay? So that's how it measures the distance of one from the other. It's always positive. There is no reason why it should be symmetric, because I'm asking how something is distinguishable from a given hypothesis. Later, when I derive it, it's going to be even more clear why it's not symmetric like distances. A second example. The second example is consider not the real line, but an interval, 0L. In an interval, there's a distribution one can consider that is the uniform distribution. This one doesn't exist on the real line. No, because otherwise, when you normalize it, you will get that there's probability 0 everywhere. So put boundaries, a box. There's a notion of a uniform distribution that you could consider it as your null hypothesis. I don't know anything except that the particle is somewhere in the box. And then compute the relative entropy of your probability distribution with respect to this null hypothesis. You do the calculation. The first thing that you notice is that you just get an L here that makes this piece make sense. Log of P times L now makes sense. And often what everybody does is you write something that makes perfectly sense as the difference of two things that are ill-defined. Log L doesn't make any sense. Log 1 meter, I don't know what it means. And the second piece that is the Shannon entropy of the distribution. And as long as you can use the second quantity only by asking questions about variations, then in variations, this is a constant and disappears. And the second one is the one that we often use. So I'm giving you a message. If you want a quantity that you know that is going to be robust and have a meaning, the quantity is not this one that you often find introduced. Really, it's much better to start from this one. You have to declare what is your null hypothesis. Sometimes the null hypothesis is completely clear, uniform distributions. Other times it's not clear. Sometimes it's a good idea to say thermal state. Sometimes generalized Gibbs state with all the conserved quantities that are needed. But you still have to declare it. Like choosing uniform doesn't mean that you haven't chosen it. You have still chosen it and you're not saying it. Okay? And so in this sense, when you see this difference, it makes sense to think of it as an information gain. How much information did you gain by going from the probability distribution uniform to this other one? Okay, comments? Should go back to, this is all I wanted to say about the definition. Let's just go back to this one. Yes.
This is a pedantic question. But
Good.
are there times when this is not a well-defined quantity? Are there probability distributions for which the relative entropy is not well-defined?
There is a condition where one could say it's not well defined, but it just means that it's infinite. That is, if you take the relative entropy of something with a large distribution with respect to something with a narrower distribution. These are clearly distinguishable. In fact, S is infinite. Sometimes people will say infinite means not well defined. And so you find conditions under which this is not well defined. But I would say it's still telling you something significant. Okay? Okay, let's go back to this. Most of you were saying this one. Some of you were saying this one. We clarified that this one, yes, in point-wise, this is the farthest away. But the kind of questions that we are asking, they are more measure theoretic. I did put in numbers. So clearly this one has the subdistance largest, units meter to the -1. The number doesn't mean anything at all. If you look in L2 distance, the distance is 0 because the measure of this point is 0. Okay, it's just 1 point. Of these two, the L2 distance happens to be slightly larger for this one, but still units of 1/square root of meters. I don't know the number with meaning it has. That's no meaning. Somebody was suggesting check moments. I played with it and I made these two to have exactly the same standard deviation, same variance. So they happen to have the same variance, the reference one at variance 1. And so if you just measure variances, these two are equally far, but we had the intuition one is farther away. Okay, let's go to relative entropy. This one is 1 bit away, and this one is 2 bits away. 0.69 and twice as much. Okay? So I've given you the definition. Now we're familiar with the definition. We can do the next step. Are there comments before I go to the second part?
You already mentioned this, but why are we using Bianchi?
It's a common way of talking. I will not convert it. I'm happy with having this number. All the point is, once you have the number, what do you do with it? I'm going to show you what to do with it in a way that it's not useful to convert it in bits, but okay. So this is all the story of, do you like to think binary and computational, and every log is a log 2, and so you find all this literature where log always mean log 2, and exp x always means 2 to the x. Which confuses every formula if you are not aware that exp means 2 to the. Okay? Okay. Yes.
In the definition of relative entropy, you have to somehow subtract from your integration space where P0 is 0. Right?
Yes, I have to be careful with that. And so there are some hypotheses P0 for which this quantity is infinite. That means that if my hypothesis says that there's nothing there, and then I find something there, I can immediately tell that my hypothesis is right. And so mathematically, you are right. I have to impose it is never 0. But if it was 0, it's telling me something meaningful. It's telling me that they are very distinguishable.
Yeah, however, you don't have any distinction between something that is very different and relatively.
Yeah. Yeah, infinitely
You
different.
have infinite for both. For
Yeah.
something that is very tiny, where a P that is very tiny, where P0 is 0,
Yes.
or a P that is huge.
Yes.
They are both in.
And that's exactly the point. And so now I have to convince you that this is the correct number that you want, because this is the number that helps you test the hypothesis. If you want to exclude that hypothesis, this is the kind of question to ask. Okay? Next step. Part 2, hypothesis testing. And so we have the formula. If you make measurements and you place them in bins, this becomes a sum, probability of being in one of the bins. And now we can ask this question of how does this quantity measures the statistical distinguishability of a sample generated from an hypothesis from actual data that have some frequencies. And I just want to convince you really that these things are concrete, they are useful. I brought a box of nails. You measure the nails. On the box of nails, you find the average, 31.80 millimeters. You find the standard, ASTM something, that tells you what is the standard deviation, what's the probability distribution they are certifying. They say it meets or exceeds this standard. And so if you believe what's written there, that's your null hypothesis. What's written there is that you have a given nominal length and given nominal standard deviation. If you believe that hypothesis, by choosing bins of given size, you could generate a sample out of that hypothesis. you're not going to get a Gaussian. When you generate a sample, sometimes you find a bit more here, sometimes you find a bit less there, right? There can be deviations, are just statistical deviations from the probability distribution, okay? And so 31.80, 80 millimeters. This one, for instance, predict that there are what, like 15% of the nails less than 31 millimeters. And if the box is 200, there should be about 30. You can check it. This is about 30 nails. Okay? Okay, but we have actually the box, and you can do the work. You just measure them one by one. Let's check one.
Did you actually measure all of them?
Twice.
32.20 millimeters. And this is the data. This is the data. Okay? There's quite a few here. There's quite a few here. That means that the machine was probably calibrated at the beginning to that standard. But then does it really meet that standard, or can we exclude that the box meets the standards? You know, given this data, well, you can compute now the relative entropy. You find that it's 1 bit away. And the question is, what does it tell us? No, that's a number now. Comments before we go ahead? No, now we want to understand how likely it is that this set of measurements, that is this histogram, where I found 40 nails that have 32.40 millimeters, how likely is that the sample is one of these generated out of the hypothesis? Yes.
So you just compared this distribution with one of the three.
I compared this data to the promise.
To the continuous distribution.
Yes.
Yes.
Yeah, so I took the continuous one, I made it in bins, so it's this red line, and I compared it to that. So this is the thing that you can compute pen and paper, or maybe you code it. But the question is, can you measure it? What would you do to measure it? This is a question that comes now and again. You can compute the entropy, but can you measure the entropy? In thermodynamics, we measure entropy differences, but now we want to make sense of entropy, not in a regime, the thermodynamic regime, when you change energy at fixed temperature, but for something that's very far from equilibrium. Can you make sense of some? It has to be a statistical measure. This is the one that I'm trying to convince you that it's concrete, it can be done. So what is it? Well, let's phrase the question carefully, and then we do a computation. So I have 1 page of computation, of theory, to convince you of that formula. The question that I'm asking is, what's the probability of excluding the standard, the ASTM, and doing it incorrectly? Because in fact, it could be that this one is just a statistical fluctuation that happens to be larger than those, but still likely enough that it could happen. So I look at it and I would say, well, it doesn't look like a Gaussian, so I exclude it. They told me I should get the money back. Or it could be that that would be incorrect to exclude them. So how do I check that? Well, let's go through it carefully. I have the data. It's a sequence of measurements, n measurements, 220. Each measurement falls in some bin, 0.20 millimeters. I can plot an histogram that counts how many nails in each bin. Clearly, the sum of nails is fixed. And now I can ask, given the hypothesis that the probability is the promised one, P bar, to fall in a bin, what is the probability or the chance that this hypothesis generates the histogram of data? Well, you can do it brute force. You just check the number of histograms that come from this probability that look like the data divided by the total number of histograms, a fixed number. This ratio, if you were really to do it, these are huge numbers. But if you were really to do it, this ratio would give you the probability that this thing happens for some good box of nails. So this question is a standard question in statistics. It's the multinomial distribution. What's the probability that one given sequence appears? It's probability of being I to the power occupation number. How many sequences there are in each histogram? You count the number of sequences at fixed histogram. It's this multinomial. So this is the predicted quantity. Okay? Now, can still make a step because this formula is not very readable. And after all, I'm only interested in asymptotic properties at large number of a large sample size. So how do I do it? I do asymptotics. I do Stirling approximation. I have to be careful if you ask every time you do these things, you are doing large sample, but don't refine your bins. If you do it in mathematics adjusts the number of bins to the sample. That's not the mathematical statement. You fix the bins and then you increase the sample. Okay? In that way, you make sure that these ratios are fixed and you're doing the correct scaling limit. In that limit, you this Ni, this is by definition is N times observed frequency. So now I can do large N. You get this piece in large N, this piece that you recognize, plus a subleading term, subleading from Stirling. Okay, this quantity is what we call relative entropy. This one appears here. The probability that that histogram appears is e to the minus number of nails times relative entropy. Okay? And this thing is important. It has a name. It's called Stein lemma. When you give a number, the relative entropy of this probability with respect to that hypothesis, what you are measuring is this asymptotic scaling. Okay? Yeah, so let me say it in words.
Sorry, so
Yes.
N is the number of nails,
Yes.
and you need to do the same thing. This is the probability that for a given box out of having done this with infinitely many boxes.
I don't need infinitely many boxes. I do one box of n nails,
Yeah.
but I'm promised a distribution. So the one that I'm promised, that one I need, it's this one, the reference one. Okay? So you see it's not symmetric. This is a probability, and this one is a frequency. This one is, this PI is sample data. This one that goes here. And this one is given. Okay? And this N is not in the standard. The standard doesn't know how many nails there. It's only the box that makes it. Good?
Yeah.
So let's make it concrete. This is a way of making it concrete. If instead of doing the experiment and checking how often this happens, how likely it is that this large statistical thing happens, so that if it doesn't, you would exclude the hypothesis correctly. You can compute just this number, and this number tells you how many measurements we need to distinguish the data from the hypothesis. Just because, you see, yeah, this quantity here, you want to check when this quantity is small, exponentially small. The relevant ratio to check, or the relevant quantity to check, is this product. So if you want 1 over S is the number of measurements you need to make. If S is small, then you really cannot distinguish one from the reference. You will need many, many measurements to tell them apart. But if it's large, one measurement and you're good. No, if there is one measurement that gives you something that's completely different from the reference probability distribution, you immediately know that you can exclude the probability. Okay, so I would say this is as concrete as it can get. Are there comments before we go ahead? Yes.
When you say measurements, you mean the number of boxes.
Then, yeah, or the number of nails.
Number of nails.
Number of nails. More comments? Yes.
Could you group that to how you define the relative entropy for discrete distribution?
Yeah, yes. Okay, so let me go back. So I wrote the formula here.
Oh, okay. I see.
If you want, it's the one before by binning it, by saying I cannot tell if it's in this bin on what side of the bin it is. So it's just a piecewise constant thing. Okay.
So
So if you start from this, you can take the other as a limit, or if you start from the other, you can think of this as
for
constraint.
small lengths, you will have fluctuations in SPP. Because you are not in the limit of your approximation of this, length, right, right.
This is important.
So somehow you have to, even if the 1/s tells you one is enough, if the 1/s tells you one is enough, you say, no, I have to calculate this better.
Yeah, exactly. Yeah. So if you get this one close to one, you are. If this one is much smaller than one, it's yeah. If this one is much larger than one, good. But if it's about one, then be careful. Go check the next order, because this is a log. Doesn't go down so quickly. Log n over. Okay.
Yeah.
This is the kind of thing that is often hidden because one says it's approximately that, but when you derive it, you see what this is. Yes.
How did you determine the bin size? Did you just pick one or was there a Sure.
When I did it, so a vernier is 0.05 millimeters, and just to be careful, I put 4 of those together, so 0.20 millimeters, and then I stayed with that.
The problem will be to explain this to the manager at Lowe's.
Ah. Yeah, if you check how they make them, they have a procedure that should explain why it's like that. Okay. You can calibrate it once, but then, but yeah, you have to explain it. Yeah, but the standard, if you go through the document of the standard, is very careful in what is acceptable and what is not acceptable. Okay, I go ahead. Let's do it for classical mechanics before quantum mechanics, because it allows me to clarify a step that then gets mixed up with other things when we do the quantum one. Many of these questions make sense for classical mechanics, and then quantum mechanics adds an additional surprise. Jonathan.
Can I ask one more question?
Yeah.
So when you bin it, you introduce a new size, like
Yes.
length into the problem. Does what you're saying about the number of measurements, also for when you talk about them, you're measuring entropy in the natural.
Yes.
Does it change anything about it?
Okay, let me address first natural versus binary. So if here I put natural, you get natural. If here I put log 2, you get a 2. So in the end, what is independent of the logarithmic units is this probability. Okay? So yeah, it's where we split it when we get a dependence on log 2 or natural or binary. Then you were seeing bins. If you are able to send n to infinity in fixed bin size, you're always good. Now the problem is that I had just one box and finite patience. So I had to choose something reasonable. If it was too large, it was useless. If it was too narrow, I couldn't trust it. But that remark is important. You need b fixed and then to infinity, not b as square root of n. Otherwise, none of this makes sense. Okay. Classical mechanics. Now what relative entropy is, it's clear. So I'm going to assume all of that and add some physics. I'm going to post as a puzzle again. The puzzle is, I have a free particle in one dimension. The state of the system, well, it's not a point in the space. The state of the system, I have to prepare the system. I have some apparatus that prepares the system with some finite resolution. The state of the system is a probability distribution in phase space. Question, what is the entropy of this state? So, first step is the first step clear to everybody that comments on this. A state of a classical system, a state of a quantum system is a vector in Hilbert space. A state of a classical system is a probability distribution on phase space. It could be a delta, it's one example of a state, but there's a full linear space of states. So I'm taking this state. I'm asking, what's the entropy of the state? A bit as when we ask in quantum mechanics, what's the entropy of this density matrix? Okay? And there's a natural guess, the one that we might have learned somewhere. The natural guess is just do the Shannon entropy or the entropy you integrate in phase space minus P log P.
Not important. What is the subindex or the subscript in the S?
It's a star to mean I have a thing that is well defined, that is S. I'm going to write it as the difference of two things that don't make sense. This is the thing that doesn't make sense.
Yeah.
And I need a star to remind myself. Not to...
That was the L.
Exactly. Exactly. So remarks. First, is it well defined mathematically? And second, is it meaningful physically? So mathematically, there are all the objections that we had before. Here, there's a log. It's log of 1 over action. I don't know what that means. Is it invariant under coordinate transformations? Well, here we happen to be lucky. Suppose that you take a canonical transformation, a mapping phase space that sends QMP into some new QMP. When you do the change of variables, you get Jacobian as before, but this now is 1, because canonical transformations preserve a phase space volume. Okay? And so it turns out that this entropy, this Shannon entropy on phase space, is invariant under canonical transformations. So this is nice. It still has this problem that it depends on the units, though. So the value, I don't know what it means. Then is it physically meaningful? How do we measure it? And all my attempt with the nades before was, when you say entropy, if you mean relative entropy, you can actually measure it. It's not easy at all. It's a statistical measure. You take a sample and compare it to some hypothesis. And then there's something you can measure by just counting how many histograms look like one generated from the hypothesis. Okay? So the message is, take relative entropy as the one fundamental quantity, and then everything else comes as special cases. Comments before I go ahead?
You need to find the P0.
I have to postulate a P0. So I'm going to give 2 examples, 2 hypotheses. The first is take a free particle confined in a box of size L, but I also know that to prepare it, I have a fixed maximum energy. The energy cannot be larger than Emax. And so there's a natural null hypothesis that is the uniform distribution in here. If I don't fix the energy, this is infinite volume, doesn't make sense to say uniform distribution. And so now I can say, well, prepare a state, for instance, by taking a ball or putting it on top of something. This could go one way or the other. So the probability distribution has a peak here and a peak here. It's a mixture of 2 Gaussians. And you can compute the relative entropy with respect to your uniform hypothesis. And you find the difference of 2 things as before. This is log action. This one has the same problems as before. But the difference between the 2 is well defined. And the difference between the two is the one that has a meaning in terms of hypothesis testing. If I was to repeat this experiment many times, collect data, I can ask the same questions as before. How do we measure it? Well, repeat preparation many times. Each time measure in which bin do you end up in phase space. The probability of incorrectly excluding the uniform hypothesis because of some large statistical fluctuation is e to the minus n relative entropy. And so out of that value, you can tell how many measurements you need to distinguish them, exactly as before. This is essentially all you need at the classical level. There's not much more. Other comments? Yes.
So, if we look at states in this sense of probability distributions and things like that, it seems like all you've done, and I mean, you've shown that it also doesn't depend on canonical transformations. But it seems like there might also be some notion of distance that I would want if I have a metric structure on phase space. So this makes no reference to that at all, right? So if I have a canonical transformation, for instance, shears two probability distributions to be extremely, different from each other. How does it seems like it doesn't necessarily
Good. Yeah. So it's a good point. There is no Euclidean metric in phase space. You cannot ask what's the distance between 2 points in phase space. There is no object that tells you the distance between points in phase space. You can only measure symplectic areas. And this quantity depends only on them. So it's a good property. Now, here as example, I always made the example with respect to the uniform state. I could have compared to other things. Next time, we're going to look at thermalization. I'm going to compare to Gibbs state. Asking if the system thermalizes is asking if in time, the relative entropy of a subsystem with respect to Gibbs approaches 0. Becomes much smaller than 1. Okay? And this should not depend on additional quantities. It's just a question of, does the system thermalize independently of additional structures? Okay, all this was classical. I did it first. Nails. Nails are not classical. There's no phase space. No, this is just like data, measurement of things. This one was physical system, classical physical system. I could ask how these things evolve in time. I'm going to do it next time. Now I'm going to take another physical system, but quantum mechanical. Because I have to show you something that is non-trivial and is worth commenting on. Okay, so last part, relative entropy in quantum mechanics. I'm going to take an example that in this course we have discussed at length. As usual, the computation is easy, it's immediate. In fact, in many ways, quantum mechanics is easier than classical mechanics. You don't need to know measure theory, you just need to know matrices doing these things. But physically, there's something highly non-trivial that I have to clarify. So as a system, I'm going to take a spin 1/2 object. Let's say a silver atom, a neutral silver atom, the valence electron in 5s as a spin, can be, you put it in a magnetic field, it splits, it can be up or down. I prepare the system in a state given by some density matrix. Let's say matrix written in the basis of spin z in a magnetic field in this direction. And I can compare, for instance, to the hypothesis of, there's a notion of average state, no, the so-called maximally mixed state. So there's a well-defined question that is, what's the relative entropy of this state compared to with respect to this hypothesis? I'm going to put the word quantum here and write a definition. The definition is, check if you recognize the one that we already had before. This definition is doesn't require this rho bar, it's general. Trace of rho log rho minus rho log rho bar. There's a minus, I can think of it as rho bar to the -1. So this is rho over rho bar or rho bar to the -1. Okay, so the same formula as before. Still, people like to write it this way so that you don't have to invert matrices, but it's the same calculation. If you were to put in that rho bar, you see that you just get out a log2 that is log dimensional Hilbert space minus a quantity that is the von Neumann entropy. And now, because of this is a two-level system and we are not working, because this is so simple, that's the way to say it, this quantity looks like it's well defined, and it's what people often use, the von Neumann entropy of the density matrix. But don't forget this piece. The two always go together. In fact, it could happen that the dimensional Hilbert space is infinite, an oscillator, quantum field. Then what do you do with this? And there's also the question of how do we measure this quantity? I gave you a concrete way of thinking about the relative entropy, how to measure the relative entropy as a statistical measurement of distinguishability. But that requires this piece, requires the hypothesis. Often we make the hypothesis that the Hilbert space is finite dimensional, and we don't know anything about the state. So here we put log dimension, and then we ask only questions about the difference in relative entropy of different states, as for instance in thermodynamics in an adiabatic process, delta S equal delta Q over T, and that delta S, this piece disappears, you get only this one. Okay? So the thing that I haven't done is to tell you how to measure it statistically, as I argued for histograms. And that is where there's something new. Are you still with me? Okay. So time is good. I'm going to take 5 minutes to cover a technical result. I'm going to go through it. I want to show you only what enters, only why it's non-trivial. Again, let me make it clear as I can. I cannot do it for one spin. This is statistics. I need many spins. So let's do Stern-Gerlach with many silver atoms. I have my oven at 1,000 degrees. I have a collimator. I have a 1 Tesla magnetic field that splits them by a couple of millimeters, the beams. Then I can do counting. If I just do that, well, there's something to appreciate. First is that if I do it one by one, if I have this collimator such that I get 1 silver atom at a time, I still cannot measure for each one of them Sz and Sx. They don't commute. There are Heisenberg uncertainty relations for them. So if I want to collect statistics, I have to prepare and measure this one, do statistics of this, then prepare again and measure this one and do statistics of this, and then collect the statistics of all of these things. That's the first non-trivial point. There's a second non-trivial point that doesn't arise in classical mechanics. The second non-trivial point is that once I produce a sample of n atoms, so I'm not doing one atom at a time, I'm going to do n altogether prepared. Then I have access to a new class of measurements. They're not single atom measurements. I could measure a collective quantity like the total spin. And this collective quantity, among the possible measurements of this, one is the average magnetization. That's completely classical. But there are others, like I could check the projection on this entangled state. This one doesn't exist classically, this measure. This is a genuinely many-body measurement. Okay? So once I produce many, I can distinguish measurements that are repeated on every single one, but also measurements on collections. Okay, so having highlighted these 2 points, now I can show you what is the non-trivial thing, or how you take into account these collective measurements and why they are important to give an interpretation, to give a meaning to the relative entropy. Let me say it again. If you choose a basis of observables, then we are just asking about classical information. we don't want the probability of outcomes of measurements or the entropy of outcomes of measurements. We want entropy of the state, including all possible observables, the full algebra of observables. And so to understand that, one needs a result that is non-trivial. Petz was the one who really clarified the ingredients. You find it in chapter 8, quantum Stein lemma, also illustrated in these lectures of Witten, at the end of the lectures. I'm going to show you the two ingredients. So these are the technical ingredients that you need. The first technical ingredient is immediate. If you have n copies, the relative entropy of n copies is just n times the relative entropy. Easy. The second is less trivial. The state and the hypothesis, as matrices in general, they don't commute. However, if you take it tensored many times, in a very specific sense, the commutator is negligible. I have to say in what sense, what I mean, negligible in this statistical sense, negligible in this n to infinity limit. So here's the mathematical statement. Take the relative entropy, this one that I was speaking about before. Now, this is invariant under unitaries to the left and to the right, exactly as classically was invariant under canonical transformations. So I can consider a unitary that puts my reference state as a diagonal matrix. This is not 2 by 2. This is 2 to the n times 2 to the n, diagonal. And then this one is not diagonal. However, I could project it on the diagonal part. And then this quantity is different from this one. There's an inequality. The thing that you can check is that the difference goes as log n. The proof is nice, it's group theoretical. You just look at the dimensions of the reducible representations of the permutation group of n. But that takes tools that would take an hour to go through them. We could, if you ask me, but not now. This is the log n. But now this is diagonal and this is diagonal. So these are classical relative entropies. Oh. Okay? It is a list of probabilities, 2 to the n probabilities. So now I can take these 2 points, this one, and say the relative entropy, the quantum relative entropy, is 1 over n classical relative entropy of collective measurements of n up to order log n over n. For this one, I have the classical Stein lemma, and now I've learned the quantum Stein lemma, or the what should be called the Petz theorem. It is the probability of incorrectly excluding the hypothesis is e to the minus classical relative entropy, classical Stein lemma, that is e to the minus small n times large n. Small n is the number of repetition of collective measurements of n. It's this product that is important in the quantum theory. And this is called quantum Stein lemma, and it's something in the last 10 years has been really central in quantum information. So if you want an interpretation of this relative entropy of 2 states, how many measurements do you have to make? 1 over s. But what kind of measurements are they? They are not just repetitions. They are of this kind. You need collective measurements repeated.
So informative means how many speeds the measurement should involve.
Yes.
So if you are going to decide to do only single speed measurements, your end will have to carry the work. You can only fix the same.
Yeah. So I need, for the proof, I need that they are separately large over there. Separately.
I see.
Yeah.
I see.
Yeah, it's this species.
Yes, I see.
Okay.
But yes,
Otherwise, you get an inequality.
Yeah.
You say, choose a set of compatible measurements. The classical relative entropy bounds from above the quantum relative entropy. So in a sense, this is the proof that you can saturate that bound, but to saturate it, you need collective measurements. And
You give me that, sorry, you are making a question, I like to. Intuitively, what you are saying is that you want to somehow capture all entanglement. And for that you need to measure more than a single spin.
You can make these measurements that are not single particle measurements, that if you were to restrict them to single particle measurements, they would be this POVM. The theorem I use only projective measurements on an isolated system. I'm not allowing anything else. Okay.
So, sort of theoretical question. In the setup that you had.
Yeah.
The study that
Yes.
you have n particles, right?
Yeah.
You do measurements on each of them, uppercase n. And then that is how you get the collective measurement, right? You're not doing a one-shot experiment, a one-shot measurement in the sense that you're not measuring the total angular momentum.
Yeah.
Or something like that, right?
Yeah. So I can use the apparatus to prepare, but I have to change the apparatus that measures.
Sure, but you're still not doing a collective, sorry. When you say you're doing collective measurements, you're doing a measurement on each particle.
No, okay. Suppose that I prepare them. I prepare many, all the same preparation. Okay, so the state is rho, tensor rho, tensor rho, tensor rho.
Uppercase n.
And now I make a measurement, and my measurement is a von Neumann projective measurement, but it's not a measurement on one without touching the others. It's a collective measurement in the sense that it's the simplest example is if you have just two, I can check if they are in the singlet state. Okay? I cannot make this measurement by doing one first and the other after.
Yeah, that's what I want to ask.
Yeah.
You're measuring everything in the singlet or not?
Yes. Yes. And that's why in the proof representations of the permutation group enter. You have to count how many of them there are.
Because they can get entangled, you won't be able to make each state.
More comments?
But in that experiment, will they be entangled? Just because, are they interacting with each other? It's not.
No, the preparation is, the state is not entangled.
Yes.
Just rho, tensor rho, tensor rho, tensor rho. But the measure, but I don't know rho. I only can make a measurement and ask what's the probability of outcome of that measurement, or what's the frequency of outcomes if I repeat many times. But I'm allowed to make measurements that are not one-body measurements. Measurements that after I've done the measurement would entangle rho. And this is the one thing that is not there at the classical level. All the others, they are there. The thing that is not there at the classical level is, at the classical level, you have a commutative algebra of observables and states on a commutative algebra of positive linear functions that are probabilities. If you have a non-commutative algebra, states are positive linear functions on that algebra that are vectors that can be represented as vectors in a Hilbert space. And so you have a new phenomenon that is entanglement. And this relative entropy, the quantum one, captures also that. Okay, so that's all. Questions left to address? Many. One is, I never spoke about subsystems. Next time I'm gonna say what I mean by entropy of a subsystem. I never said anything about time evolution, but the classical system and the quantum system were dynamical system. I can ask how the entropy of a subsystem changes in time. And we can ask about thermodynamics. Does it thermalize? So this is gonna be on Friday. And that's all for today. Thank you.
So when you have relative entropies, right, like the one element might not be well-defined things, but we know in the QFT aside, right, you can have situations where the partition function goes up, but the correlation function is still a well-defined object because you have infinity cancelling now. Is that still something that can be done? Then for relative entropy, does it happen that your one element entropy is not well defined, but because you're sort of taking a inverse of the rho zero, we can still compute relative entropies. Even for systems which are not finite dimensional.
From the way I described it, if this, what you said, it's not well defined in the sense that it's infinite. What I learned from the fact that it's infinite is that it's very easy to find a measurement that disproves the hypothesis. That's what I conclude out. So I don't take it as ill-defined, but as a very suppose that I open this and I find one that is 5 centimeters. The relative entropy is infinite. But that just means that I know immediately that there's a problem. And yeah, so that's this one, you choose it. And in Bayesian reasoning, you start with an uninformed prior, and then as you go ahead, you can refine the prior and ask better questions. So if you find that it's infinite, you learn that you have to update this and put something better, and then you ask again the question. So in that sense, this is something that you always have to declare. And once you have declared it, then the quantity becomes easier. Okay? And there are all of these issues. So when you apply this to quantitative theories about algebras that are not type 1, that are all about under what conditions one piece is well defined, the other piece is well defined. But this one is well defined. This one is always well defined.
So it's well defined.
Always well defined with this caveat of
Yeah.
good.
May I make a comment that goes
Yeah.
back to the beginning of this discussion?
Yeah.
I think it's more than ever convinced that it's a distortion to talk about relevant because, I mean, it's okay to motivate this, but it's a distortion to talk about it as measuring distance between probability measures. Like,
It's not that
it's
easy.
asymmetry, which looks at first like just a niggling little technical thing, but really, when you're saying I have a reference. And I'm evaluating the second probability
Yeah.
measure by standards which are determined by this reference, which is really the thing.
Completely.
And I mean, to make, but, I mean, sort of to pile on top of that.
Yeah.
There is a good metric on probability measures, it's a total variation metric, which you mentioned.
Yeah, I
This-
didn't.
This L2
Yeah.
thing of the densities, that's rubbish, but
Yeah.
the total variation metric is a good metric.
Yeah.
And
But it's not a statistical measure of distribution. So the point that I made is I'm not interested in a distance. One can look for distances.
Yes.
It's not, you are abstraction and you define distances. Here we are interested in entropy.
Yeah.
If you're interested in entropy, this is a concrete definition of what entropy is
right.
away from thermodynamics.
Sure, I'm not, it's not a knock on nation relevant. The same, you know, we started out.
Yeah.
with-
So you could add in this list all the things that are distances that would go somewhere here with these dots, like the one that you're proposing, and then one can ask, like, how does it fare?
Yeah, I mean, the nice thing about total variation is it's defined in a sort of operational way, all right? Right, you don't have to go and you look at weird formula and try to figure out what it means,
Mhm.
operation.
Mhm.
Yeah.
Does it have a thermodynamic interpretation?
Well, it seems more. It attuned to quantum measurement somehow. I mean, it seems like it has a good quantum version, but no, yeah.
Yeah,
I love that.
Can you say
Yes.
what's the metric you're telling?
Oh, so I have two probability measures and the distance between them is defined as the maximum difference in probability over overall possible events. So I'm gonna pick an event, but think about picking all possible events, right? And you look at the difference in the absolute value of the difference in the probabilities, and you pick one that maximizes it. So it's sort of like saying, okay, you did one test. There's the best test to distinguish between these two.
yes.
In the formula that you have that relates the entropy of classical and quantum, can I think of that as like for a given system, I have some amount of classical entropy and some amount of quantum entropy, or do I always have to think of a system as purely quantum or a system that is purely classical? Can I have like two different ones and they have like a limit from quantum to classical.
I would say for the quantum system, there's only the quantum one. There are other things that one can ask that is consider a subsystem. It has an algebra of observables that is commutative.
Mhm.
What's the entropy of that subalgebra? This is what we would call the classical. And one can do that, but then you have to add in the list of relative entropy of state, reference state, and subalgebra, which was not an ingredient today. There's an additional ingredient in there.
But probably when I was listening to this question, if you scroll up a little bit, there will be a formula where you have the there.
Mhm.
So let's say that somehow that's the classical part. In terms of
Mhm.
patience and the other is the one that comes from the fact that we have off diagonal terms.
Yeah.
Because the log n came from off diagonal terms.
But this would be classical collective measurements, not single atom measurements.
Ariel, these are the diagonal elements of your collective n particle density.
Yeah.
These are the occupation. In some
Yeah.
basis that you
Yeah.
choose based on
Yeah.
your process.
Yeah.
Maybe, yeah. So you object to the idea that it separates classical.
Oh, no. Oh, yeah, I object. This one is not the classical relative entropy. This fact that this is the classical relative entropy is you prepare one object, you make measurements on this one object, and you repeat them many times. This one is not throwing. Oh, now I understand the question. This one is not throwing away the entanglement part. The entanglement part is in this exponentiation. So this one is not classical entropy. You can check, for instance, by taking states that violate Bell inequalities and seeing how this one shows it. So it neglects something, but still captures quantum properties. This is still quantum relative entropy. I think that's important. I'm gonna keep answering, but we are out of time.
So just like a more general question, in this course till now, we have been talking about entropy.
Yeah.
Like one Neumann entropy, and relative information, etc. And these have been information theoretic
Yeah.
quantities.
Yeah.
Which tell us like what happens to
Yeah.
this system, we don't know about the environment. Except for, I think, the presentation before lecture, we have not connected this to physics, like the entropy that we usually used to.
That's correct.
Because these have not been, as of yet,
Yeah.
connected to physical observation.
Only
In the sense of-
statistics of outcomes.
Yeah.
Next time there's gonna be thermodynamics. That's the plan. Okay, that's all for today. Thank you.